You are standing on a rooftop in July. The air reads 104 degrees Fahrenheit. A thin panel at your feet measures 10 degrees cooler. No compressor, no wires, and no power. The sky is pulling heat from that surface and sending it into space. Persians froze water this way 2,000 years ago. Tonight, a family will turn a utility bill face down. That is their share of the $29 billion spent cooling American homes every year. At the end of this video, you will know how this forgotten science works, how to build it yourself, and we will show that tape and aluminum foil dropped a surface 20 degrees Fahrenheit below the surrounding air. I drove to Red Bluff, California last summer, a small town in the Sacramento Valley where highs regularly exceed 105 degrees. A local supermarket let me onto their roof. 80 reflective panels sat up there, manufactured by SkyCool Systems. No fans, no compressors, nothing moving. I placed a surface thermometer on one panel. In direct sunlight, it measured below the air temperature around it. The California Energy Commission confirmed in 2025 that this array rejected 30 to 45 kilowatts of heat. That supermarket removed the rooftop water sprinkler it used to cool its condenser. They save tens of thousands of gallons every year on a grocery store roof in a small California town. Here's what they never told you. A retired HVAC contractor in the same valley showed me his workshop roof coated with a high-concentration calcium carbonate paint. Inspired by research from Purdue University, his workshop stayed measurably cooler than his neighbor's identical structure with a standard dark roof. No permit pulled, no contractor hired. Materials cost under $50. What I saw was not theoretical. It was running on real buildings for almost nothing. But this science did not start at Stanford or Purdue. It started in the deserts of ancient Iran over 2,000 years ago. Persian engineers built underground structures called Yakchal near the city of Yazd as early as 400 BCE. They filled shallow pools with water on clear winter nights. Tall mud brick walls shaded those pools during the day. Before sunrise, the ice was harvested and stored in domed pits, sealed with a compound called sarouj. Persians built it, Egyptians built it, Indian villages built it. The physics is the same. Every surface on Earth radiates heat as infrared energy. On a clear night, that energy escapes through a gap in the atmosphere between 8 and 13 micrometers wide. Scientists call it the atmospheric transparency window. Through that window, heat travels directly into outer space. In dry desert air, this effect freezes water even when the surrounding air never drops below freezing. The Persians did not have the vocabulary, they had the physics. Read that again, they made ice in the desert, no electricity. But nighttime cooling is just the beginning. The real breakthrough pushes past darkness into the one problem scientists said could not be solved: cooling a surface below air temperature in full direct sunlight. In November 2014, Aswath Rahman and Shanhui Fan at the Ginston Laboratory at Stanford University published a paper in Nature. They built a multi-layer photonic structure that reflected 97% of incoming sunlight while emitting strongly in the atmospheric transparency window. It cooled nearly 5 degrees Celsius below ambient air in direct sunlight. Zero electricity. In April 2021, Professor Julien Ruin and his team at Purdue University created the whitest paint ever recorded. It reflected 98.1% of sunlight using barium sulfate particles. Covering 1,000 square feet, delivers an estimated 10 kilowatts of cooling power, more than most residential central air conditioners. The paint entered the Guinness World Records. Now here is the part that changes everything. The universities proved it, the commercial installations confirmed it, the California Energy Commission documented it on a working building. So the question is not whether this science is real. The question is why it is not in a single residential building code in the country. The answer involves money. The HVAC industry in the United States generates $150 billion in annual revenue. Air conditioning alone consumes 6% of all electricity produced in the country. American homeowners pay $29 billion every year just to run cooling systems. Picture executives in convention centers reviewing quarterly projections. Those projections depend on one number: the compressor replacement cycle. Every 10 to 15 years, your system fails and you write a check. A technology that eliminates that cycle threatens the entire structure. It threatened it then, it threatens it now, it always will. The Department of Energy's ARPA-E program provided only $3 million to Sky Cool researchers in 2012. Compare that to billions flowing into conventional HVAC expansion every year. Pacific Northwest National Laboratory analyst Nick Fernandez found that coupling radiative cooling with hydronic radiant systems could reduce cooling energy use by nearly 70%. That finding changed 0 building codes. The physics never changed. The economics overruled it. Now, if you do not own land, if you are sitting in a suburban house or an apartment right now, stay with me, because what comes next works in any home, costs under $300, and requires 0 permits in most jurisdictions. At the beginning of this video, I described a study that sounds impossible: tape and aluminum foil, a temperature drop that defies everything the cooling industry wants you to believe. Here is that study. In 2021, researchers Jyotirmoy Mandal and Aswath Raman at the UCLA Samueli School of Engineering published a paper in the Journal of Photonics for Energy. They built a radiative cooler from 2 layers of transparent tape applied to aluminum foil. The adhesive and film contain chemical bonds that radiate heat in long-wave infrared frequencies. Those frequencies pass through the atmospheric transparency window and escape into space. With a polyethylene convection shield, the drop reached 11 degrees Celsius, nearly 20 degrees Fahrenheit below ambient, from tape, foil, and plastic. Published in a peer-reviewed journal. That is the number promised at the start. It is real. It is published. The materials are in your kitchen drawer right now. Here is how to build a working version. You need aluminum foil, polyethylene bubble wrap, rigid foam insulation board, clear polyethylene sheeting, and duct tape. Build panels in 2-foot by 4-foot sections. The bottom layer is rigid foam insulation as a base. The second layer is aluminum foil, shiny side up. The third layer is bubble wrap laid directly on the foil. The top layer is clear polyethylene sheeting stretched across a simple frame as a convection shield. Set panels on a flat rooftop or any elevated surface with an unobstructed view of the sky. Published field tests achieved a 4 degrees Celsius reduction below ambient at summer noon. At night, reductions reached 7 to 11 degrees. Total cost per panel runs $10 to $15. Tools required are scissors, duct tape, and a utility knife. This works best in dry, clear sky climates. The Southwest, the Mountain West, the Great Plains. These panels do not fully replace air conditioning in every home. What they do is reduce the load your system carries and the number on the bill your family dreads opening. This is just one technology, but 5 more work on the same principle of replacing mechanical cooling with physics that already exists. And by the end of this video, you will know all of them. The Earth beneath every home in America operates as an infinite thermal battery. This is not theory. This is measured physics documented by laboratories and research institutions worldwide. At Oak Ridge National Laboratory in Tennessee, scientists have monitored ground temperatures for decades. Their findings are remarkable. Below 6 to 10 feet, the soil maintains a temperature equal to the annual mean air temperature of that region, plus 1 to 2 degrees. In Chicago, that means 55 degrees year-round. In Atlanta, 62 degrees. In Denver, 58 degrees. In Phoenix, 67 degrees. In Minneapolis, 52 degrees. The surface above can swing from -20 degrees to 105 degrees, and that underground temperature barely shifts by a single degree across the entire year. The reason comes down to thermal mass. Soil weighs between 100 to 125 pounds per cubic foot. Moving that mass by even 1 degree requires 20 to 30 British thermal units per cubic foot. The Earth absorbs summer heat so slowly that by the time warmth penetrates 6 feet down, the season has already changed. The soil acts as a buffer, storing and releasing heat on a 6 to 8 week delay from surface conditions. This thermal lag is why root cellars kept vegetables fresh for centuries, and why wine caves maintain perfect storage temperatures without electricity. Now here is the number that changes everything. Engineers measure cooling efficiency using the coefficient of performance. Your air conditioning unit in the backyard achieves a coefficient of performance between 2.5 and 3.5. That means for every unit of electricity consumed, you get 2.5 to 3.5 units of cooling in return. Thermal labyrinths measured across 47 installations worldwide achieve an average coefficient of performance of 28.7. The only electricity required is a small fan pushing air through buried pipes. 28 versus 3. That gap represents billions of dollars the HVAC industry would lose if this knowledge spread. But here is what makes this truly remarkable. We did not discover this physics. We forgot it. 2,400 years ago, in what is now central Iran, engineers constructed structures called yakchal. The word translates simply to ice pit. But these were not primitive holes in the ground. They were precision-engineered cooling facilities that still stand today. At the city of Yazd, you can walk inside domed chambers rising 60 feet high with walls 6 feet thick at the base. Those walls were made from a material called sarouj, a mixture of sand, clay, lime, goat hair, and egg whites that achieved insulation values exceeding modern fiberglass bats. The yakchal connected to underground tunnel networks called kanats, stretching miles into distant mountains. These tunnels, originally built to carry water, served a dual purpose. Air passing through miles of underground passages emerged at 50 to 55 degrees Fahrenheit regardless of the desert heat above. That cooled air flowed into the yakchal chambers. Archaeological teams with modern temperature monitoring equipment have documented yakchal interiors maintaining 25 to 30 degrees Fahrenheit through summers, exceeding 115 degrees Fahrenheit outside. They stored ice in the desert for an entire civilization using nothing but physics that any homeowner could replicate today. The Romans understood the same principles. At the Villa of the Mysteries outside Pompeii, archaeologists discovered something unusual in the hypocaust system. Channels designed not for heating but for cooling. Air passages extended from beneath the floors into the hillside behind the structure, creating passive circulation that pulled cool underground air through the living spaces. The Roman engineer Frontinus wrote about subterranean air passages, providing summer comfort in elite homes across the empire. Infrared thermography studies of excavated Roman cooling channels show temperature differentials of 15 degrees Celsius from surface conditions. This was not unique to the Mediterranean. In Korea, the Ondol system dates back 3,000 years. Historical records in the Samguk Sagi describe underfloor air channels that maintained interior temperatures between 64 and 72 degrees Fahrenheit through brutal summers and winters alike. In the American Southwest, native peoples built semi-subterranean pit houses for 8,000 years, utilizing earth contact cooling that archaeological evidence confirms worked exactly as designed. Every civilization that mastered hot climates discovered thermal labyrinths independently. Persians, Romans, Koreans, indigenous Americans. 5,000 years of proven engineering across every continent. Then, in less than 1 century, it vanished from Western construction entirely. In 1902, a young engineer named Willis Carrier stood in a Pittsburgh printing plant solving a humidity problem. His invention, the apparatus for treating air, became the foundation of mechanical cooling. By the 1920s, the Carrier Corporation had launched the Weathermaker campaign, positioning air conditioning as the symbol of modernity and progress. Their marketing materials explicitly framed passive cooling techniques as primitive and unsanitary. A 1930 Carrier Engineering Corporation manual dismissed earth contact cooling as suitable only for cellars and food storage. Industry publications celebrated the triumph of machine over nature as though dependence on electricity represented advancement rather than vulnerability. The machine had arrived, and everything that came before had to be erased. In 1927, the first model mechanical codes emerged with heavy participation from HVAC industry representatives. By 1945, the post-war building boom was standardizing mechanical cooling as the only acceptable approach. Passive alternatives disappeared from architectural education. The American Society of Heating, Refrigerating, and Air Conditioning Engineers codified mechanical cooling as the baseline assumption for all thermal comfort calculations. By 1980, fewer than 3% of American architecture programs taught passive cooling strategies. The technology was not disproven. It was systematically removed from professional memory. Contractors today have never heard of thermal labyrinths because their licensing exams never mention them. Building inspectors cannot approve what their training never covered. An entire field of proven engineering vanished not through failure but through deliberate exclusion. But the physics never changed. 55 degrees is still sitting beneath your foundation right now, and in Europe they never stopped using it. At the Passive House Institute in Darmstadt, Germany, researchers have monitored 847 residential earth tube installations since 2005. The performance data is unambiguous. These systems deliver an average cooling capacity of 3.2 kilowatts while reducing mechanical cooling demand by 89%. Homes maintain interior temperatures between 72 and 75 degrees Fahrenheit without air conditioning, even when outside temperatures reach 95 degrees. The average payback period is 12 years. After that, the cooling is essentially free. German building code provides efficiency credits for earth tube integration, recognizing what American code refuses to acknowledge. The technology works. In Austria, the national building standard requires thermal labyrinth analysis for any structure exceeding 1,000 square meters. At the Allgemeines Krankenhaus Hospital in Vienna, an earth tube system has provided 450 kilowatts of cooling to critical care units since 1994. 30 years of continuous operation. Maintenance records show cleaning required only every 5 to 7 years. Operating cost runs 2 euro cents per kilowatt hour compared to 8 to 12 cents for conventional cooling. In Switzerland, the Minergie certification program has documented performance data from over 200 monitored earth tube installations. A 15-year longitudinal study from ETH Zurich found zero degradation in system performance over the entire monitoring period. Swiss engineers solved the radon concern that American regulators use to block these systems. Activated charcoal filtration combined with ultraviolet treatment reduces radon to background levels at minimal additional cost. Swiss residential installation costs run 3,500 to 6,000 francs total. The pipe materials alone cost $300 to $400. 3 decades of European performance data, thousands of successful installations, exposed systems in hospitals and homes and schools operating year after year with documented results. So why does American code still treat this as impossible? Open the International Residential Code to section M161 and you find language requiring all ductwork to be constructed of materials having a maximum flame spread index of 200. There is no provision for earth contact air handling. The code assumes ductwork exists inside buildings and nowhere else. A system that buries pipes in the ground does not fit the template, so it cannot be approved. The EPA classifies 21 states as Radon Zone 1, meaning any earth contact air pathway triggers mandatory mitigation requirements. This adds $2,000 to $5,000 to installation costs, even though European systems have demonstrated radon management solutions costing under $100. The International Energy Conservation Code provides zero compliance credit for passive earth cooling. Builders receive no incentive to install systems that eliminate the need for air conditioning. The calculations assume mechanical cooling is the only path to efficiency. Follow the money and the picture sharpens. The Air Conditioning, Heating, and Refrigeration Institute spent $47.3 million on political activities in 2022 alone. In 2019, ASHRAE Technical Committee 6.8 rejected a proposal to create a performance pathway for earth tube systems. The committee cited insufficient domestic performance data while ignoring 3 decades of European documentation. Analysis of committee membership revealed 67% representation from HVAC manufacturers. The Building Officials Association of Florida formally opposed a 2021 amendment that would have recognized passive cooling in state code. Their stated concern was inspection complexity and liability. The real concern was obvious. Every thermal labyrinth installed is an air conditioning unit that never gets sold, a compressor that never gets replaced, a refrigerant charge that never gets topped off. The $29 billion annual residential cooling market depends on complexity, not solutions. Systems that cost $300 in materials and run on 50 watts cannot support an industry built on $1,000 units consuming 3,000 watts. The codes are written against you. The industry profits from your ignorance, but here is what they cannot take away. The physics works regardless of what any inspector says. Somewhere beneath your feet, about 2 meters down, past the frost line, past the root systems, past the earthworms, and past the buried electrical conduit you forgot was there, the ground holds steady at roughly 12 degrees Celsius. It does not care what is happening above. Heat waves, polar vortexes, the slow creep of climate change, none of it reaches that depth. The soil just sits there, patient and cool, the same temperature your great-grandparents would have measured if they had thought to check, the same temperature your grandchildren will measure a century from now. The Persians figured this out 2,400 years ago. At Yazd, they built ice houses and qanats that still function today, structures that predate Rome and have outlasted every empire since. The physics is older than human civilization and will outlast whatever comes next. A thermal labyrinth taps into this constancy. You bury a smooth wall HDPE or PVC pipe, typically 200 to 300 millimeters in diameter, and run it 30 to 60 meters through the earth. Summer air enters hot and exits cool. Winter air enters frigid and exits tempered. The ground does the work. You just built the pathway. The pipe itself runs surprisingly cheap for what it accomplishes, a couple $100s for the material, less than you would spend on a single month of aggressive air conditioning. The excavation costs more in labor than money, assuming you are willing to dig. 2 meters down is the sweet spot, below the frost line and into the thermal mass that does not fluctuate with the seasons. A weekend with a rented trencher or a favor called in from a friend with excavation equipment, and the hard part is finished. What you are building really is a very slow breath. Air moves through at 2 to 4 meters per second, fast enough for decent heat transfer, slow enough to actually absorb the Earth's temperature. The pipe slopes gently about a 2% grade, so condensation drains rather than pools. Stagnant water breeds mold. Flowing water finds its way out. The intake sits far from the house, 15 meters minimum, elevated a bit above grade, so you are not sucking in lawn debris and curious insects. A decent filter catches what elevation does not. At the house end, MERV 13 filtration and maybe a UVC treatment if you are cautious about mold spores. A small inline fan, 50 to 80 watts, nothing dramatic, keeps air moving when natural convection is not enough. Radon is the concern that keeps engineers up at night. The same earth that cools your air also exhales radioactive gas in certain geologies. An activated charcoal canister handles this, $40 to $60 replacement annually, with over 95% reduction confirmed by EPA testing protocols. Put a detector at the outlet and check it. Test quarterly until you understand your site's behavior, then annually thereafter. The permit question is where philosophy meets bureaucracy. A thermal labyrinth is, depending on how you describe it, either a passive geothermal cooling system, which triggers engineering reviews and HVAC code sections, or a fresh air intake with a long outdoor run, which references IRC section M1602 and raises fewer eyebrows. Agricultural buildings and detached workshops often face less scrutiny than primary residences. This is not legal advice. It is an observation about how language shapes regulatory perception. What is certain is that the physics predates the codes. The ground was cooling air before permits existed, and it will continue long after our particular regulatory frameworks have been forgotten. At Yazd, no one asks whether the qanats are up to code. Geometry matters more than the materials. Gentle curves instead of sharp bends, proper drainage slope, intake positioned away from dryer vents, compost bins, and idling cars. A serpentine layout if your property is small, a straight run if you have the space, sand bedding for stability, careful backfill to prevent settling, and marked locations so you do not accidentally dig through your own system in 5 years when you have forgotten where it runs. What separates a functioning system from a failed experiment often comes down to soil contact. The pipe needs intimate thermal connection with the surrounding earth. No air pockets, no loose fill that settles into voids over time. Some builders wrap the pipe in geotextile fabric to prevent fine soil migration while maintaining contact. Others bed the entire run in compacted sand that transfers heat efficiently and drains moisture away from the pipe surface. The goal is maximum surface area touching thermally stable mass. Humidity management deserves more attention than most do-it-yourself guides provide. Air passing through cool underground pipes will drop below its dew point on humid summer days. Water condenses inside the tube, sometimes gallons per day in muggy climates. This condensation is actually beneficial when managed correctly. The condensation captures airborne particles and carries them to the drainage outlet. The air that emerges is not just cooler but also dehumidified, often dropping from 80% relative humidity to 50% or lower. But if drainage fails, if water pools and stagnates, you have built a mold incubator instead of a cooling system. The 2% slope is not optional. Neither is the cleanout access at the low point. Consider also the thermal charging cycle. The ground around your pipe will warm slightly during peak summer use as it absorbs heat from the incoming air. Running the system primarily during morning and evening hours when ambient temperatures are lowest gives the surrounding soil time to shed accumulated heat back into the broader Earth mass. Nighttime operation allows the thermal battery to recharge. Continuous 24-hour operation during extreme heat waves will gradually degrade performance as the immediate soil temperature rises. Understanding this rhythm means working with the system, rather than demanding more than it can sustainably provide. Maintained properly, with filters changed, drainage inspected, and occasional high-volume runs to clear accumulated dust, the system can last 50 years or more. The pipe degrades slower than most things we build. The Earth does not degrade at all. What you end up with is air that arrives at your living space already tempered, already breathing at the planet's baseline temperature. Your heating and cooling systems work less hard. Your energy bills drop by a quarter to nearly half. And somewhere beneath your lawn, invisible and silent, the same principle that cooled Persian emperors is cooling you. Physics survived because physics does not care about marketing budgets or regulatory capture or industry lobbying. It simply works. It worked for the Persians. It works in Germany and Austria and Switzerland right now. And if you build it correctly, it will work for you quietly and efficiently for decades while the air conditioning industry pretends it does not exist. The Earth has been waiting. It has always been waiting.
Every ancient civilization that endured extreme heat independently arrived at the same conclusion. The Earth stays cool. Push air through enough underground mass and the ground becomes the air conditioner. The Persians proved it with the qanat and the badgir. The Egyptians proved it with subterranean ventilation shafts. The Romans proved it with the cryptoporticus. Different continents, different centuries, identical physics. In ancient Persia, as early as the 7th century BCE, engineers constructed qanats. These were underground water channels carved through bedrock, stretching for miles beneath the desert. Hot, dry air entered vertical shafts and traveled along channels lined with cold underground water. By the time that air reached the building above, it was cool enough to make desert summers survivable. Paired with towering wind catchers called badgers, these systems created continuous airflow through stone homes without a single moving part. In the city of Yazd in central Iran, a towering 33-meter wind catcher still stands in the Dawlatabad garden. It uses neither electricity nor polluting materials. It simply catches the wind and drives it underground, where the earth strips away the heat. UNESCO recognized the Persian Qanat as a World Heritage Site in 2016, not because it was a relic, because it still works after 3,000 years. The Romans applied the same technique at massive scale, building the 5,653-meter tunnels of Claudius, with shafts sinking over 122 meters deep. In Palermo, Sicily, a Qanat network built during the Arab period cooled the entire city. The famous Scirocco room in Palermo still uses water flowing through a Qanat combined with a wind tower to cool interior air today. Different empires, different tools, the same discovery. The ground below a certain depth holds a nearly constant temperature regardless of what happens on the surface. The modern version of this ancient system is called the Earth Tube. Some engineers call it the Canadian Well. The physics have not changed since Persia. At roughly 2 meters below the surface, the soil maintains a nearly constant temperature of 10 to 13 degrees Celsius throughout the entire year. Summer heat waves do not reach it. Winter freezes do not touch it. The Earth at that depth is a thermal battery that never runs out. You bury a long pipe underground. You draw outdoor air through that pipe using a small fan. On a brutal summer day, outdoor air enters at 35 degrees Celsius. As it travels through 100 to 200 feet of buried tube, the surrounding cool soil absorbs the excess heat. By the time that air exits into your home, it has dropped by 20 to 30 degrees Fahrenheit. No compressor, no chemical refrigerant. One small fan consuming roughly 50 to 100 watts. In winter, the process reverses automatically. Freezing outdoor air enters the tube, and the stable ground temperature warms it. Free heating and cooling from a single buried tube year-round. The Earth Ranger Center near Toronto, Canada uses 9 concrete earth tubes, each 20 meters long, buried 3 meters underground. In winter, the system warms incoming air by as much as 20 degrees Celsius. In summer, it cools air by 10 degrees Celsius. A 2025 study published in Scientific Reports documented yearly energy savings reaching 74% in Milan and over 60% in Palermo when earth-air heat exchangers were integrated with air handling units. The Cambridge Public Library in the United States uses 42 buried earth tubes, achieving 51 to 56% lower total energy use compared to a standard building. And the system lasts 50 to 100 years. Compare that to mechanical HVAC units that last 15 to 25 years before ending up in a landfill. So why is there not an earth tube under every new home? The answer has everything to do with money and nothing to do with science. The global HVAC system market was valued at $174.58 billion in 2025. Executives in corporate boardrooms depend on that number growing. American consumers spend over $10 billion annually on HVAC repair and maintenance. Technicians in branded vans pull into driveways every summer. The average customer lifetime value for a single residential HVAC client is $15,340. Now picture an earth tube. One installation, one trench, one pipe. No compressor to replace every 15 years. No refrigerant to recharge. No filter subscriptions. No annual service contracts. One fan that costs pennies per day to operate. A lifespan measured in half centuries. One sale and then silence. Zero recurring revenue for anyone. The HVAC business model depends on equipment that degrades, bills that recur, and replacements that repeat. An earth tube breaks every single link in that chain. No corporation in a $174.58 billion industry had any reason to tell you about it. The regulatory system finished the job. Earth tubes are not explicitly banned, but they face something worse. They are completely unaddressed. The International Residential Code contains no provisions for earth-air heat exchangers, no testing protocol, and no installation standard. When a building inspector encounters something the code does not cover, the default answer is always no. Not because the system is dangerous, but because nobody wrote the rule that says it is allowed. The primary objection inspectors raise is radon. Indoor radon exposure causes approximately 21,000 lung cancer deaths in the United States each year. That concern is legitimate, but Europe took a different path. When early installations in Austria, Denmark, and Germany revealed problems with condensation and mold from sloppy installation, the Europeans developed proper standards and taught people how to build them correctly. Earth-air heat exchangers have been common in European residential ventilation since the mid-1990s. The American response was to pretend the technology does not exist. But you do not need anyone's permission to understand the physics. Here is exactly how to build one yourself. Before you pick up a shovel, you need 3 pieces of information: your soil type, your water table depth, your local radon zone. Pull up the EPA radon zone map and find your county. Zone 1 means elevated radon risk and demands fully sealed pipe joints and mandatory post-installation testing. Know your soil. Clay and moist soils conduct heat far more efficiently than dry sandy ground. And know your climate limitations. Earth tubes are less effective in hot, humid regions like Florida, where dehumidification becomes the real engineering challenge. Use smooth wall, high-density polyethylene or PVC pipe. Minimum 6-inch diameter. 8-inch for larger homes or warmer climates. The inner surface must be completely smooth. Corrugated pipes trap condensation and breed mold. For maximum protection, use antimicrobial lined pipe. Companies like Amvic manufacture complete residential earth tube kits with 180 feet of 8-inch pipe infused with silver nitrate plus prefabricated stainless steel inlet towers, filters, and condensate sumps. Your total pipe run should measure 100 to 200 feet. Maintain a minimum 6 feet of spacing between parallel runs. Slope the entire system at a minimum 2% grade toward a condensate collection point. That consistent downhill slope prevents moisture from pooling inside the pipe. Trench depth is non-negotiable. Minimum 6 feet. At that depth, ground temperature holds steady at roughly 6 to 8 degrees Celsius year-round. Bed the trench bottom with 4 inches of compacted sand or pea gravel. Lay the pipe on that prepared bed. Backfill with granular material for the first 12 inches above the pipe, ensuring complete contact. No AIR gaps anywhere. Air gaps destroy thermal transfer. Seal every joint in the buried section. Solvent weld for PVC. Fusion weld for HDPE. These welds are simultaneously your radon barrier and your groundwater barrier. The air intake rises vertically at the far end, terminating at least 12 inches above ground level with a screened downward-facing cap. Position it away from driveways and exhaust sources. Inside the house, connect the earth tube to a heat recovery ventilator or an energy recovery ventilator. One documented Canadian installation found this combination boosted the heat pump coefficient of performance from above 3 to as high as 5. The earth tube made every other mechanical system in the house work better. Install an inline fan rated for 100 to 300 cubic feet per minute. Add a condensate trap at the house entry point and mount a MERV 13 filter on the discharge side. And install a continuous radon monitor in the mechanical room. That step is non-negotiable regardless of which radon zone you live in. For homeowners in high radon areas, there is a powerful second path, the closed-loop glycol earth tube. Instead of running air through buried pipes, you circulate a water and glycol mixture through a buried loop. That tempered fluid passes through an air to liquid heat exchanger inside the house. No radon pathway, no condensate in the pipe, no mold risk. It delivers 80 to 90% of the thermal benefit while remaining code compliant under existing plumbing provisions in every state. Heating, ventilation, and air conditioning systems account for up to half of a building's total energy consumption. Earth tubes attack that number at its root. Not with more sophisticated equipment, with less complexity, less machinery, less dependence on a grid that fails exactly when you need it most. When the grid goes down during a heat wave and conventional air conditioning dies, the earth tube keeps working. The ground does not need electricity, It does not send a bill. It does not break down after 15 years. The Persians solved cooling 3,000 years ago with a trench, a pipe, and the patience to let the earth do what it has always done. The temperature at 6 feet is the same today as it was when Sargon II marched through Persia. The physics still work. The pipe is waiting. Now you know not just why this was hidden from you, but exactly how to build it yourself.
Picture the ancient city of Yazd in central Iran. The year is roughly 1000 BCE. Summer temperatures exceed 115 degrees. There is no electricity. There will not be electricity for another 3,000 years. Yet families gather in underground rooms that feel like modern air-conditioned spaces. Above these rooms rise elegant towers called badgirs, wind catchers. Some stand over 100 feet tall with multiple openings facing different directions to capture any available breeze. These are precisely engineered machines built from mud, brick, and ceramic that have operated continuously for millennia. Here is how they work. Hot desert wind enters through the tower openings. Inside, the air passes over surfaces kept wet by water channels called qanats, underground aqueducts stretching miles into the mountains. As hot air contacts wet surfaces, the water evaporates and absorbs massive amounts of heat. The cooled air becomes denser and heavier. It falls through the tower into the living spaces below. No pumps, no fans. Physics and geometry are doing the work that electricity does today. Modern measurements of functioning badgirs show interior temperatures 20 to 30 degrees Fahrenheit below exterior heat. Ancient Egypt constructed towers called Mal-Kaf-S around 1300 BCE. Same principle, different name. Every civilization in hot, dry climates independently discovered evaporative cooling. So if engineers solved comfortable cooling 3,000 years ago, why are you paying $300 monthly to run an AIR conditioner? The story begins with Willis Carrier in 1902. He invented a machine to control humidity in a Brooklyn printing plant. By the 1920s, his company began marketing air conditioning for human comfort. This is where the business model becomes important. Passive cooling systems like Persian badgers require significant upfront construction cost. Then you are done. The building cools itself forever with no ongoing expense. Mechanical air conditioning inverts this equation. The equipment costs relatively little. The system requires electricity every hour it operates. Refrigerant recharges, filter replacements, compressors wear out every 15 to 20 years. The business model extracts payment perpetually rather than once. Equipment manufacturers partnered with electric utilities. After World War II, American building codes specified mechanical systems. Passive cooling fit nowhere in these frameworks. Architectural schools dropped vernacular building science from curricula. By 1970, a graduate could earn a degree in architecture without ever learning that buildings had cooled themselves for millennia. But the industry could not erase the physics. And in 1997, a building in India proved ancient systems outperform modern air conditioning with data so overwhelming it could not be ignored. The Torrent Research Center in Ahmedabad covers 300,000 square feet and contains zero mechanical cooling equipment. Massive downdraft towers rise above the structure. Water atomizes at the tower tops. Hot air enters, contacts the water mist, and cools dramatically. The building has operated for over 25 years. When exterior temperatures exceed 110 degrees, interior spaces maintain 78 to 82 degrees. Total energy reduction compared to a conventional building measures 68%. Construction cost ran about 7% higher, but within 4 years, the building had paid back its entire construction premium. Yet drive through Phoenix or Las Vegas today and count the buildings with cooling towers. You will find almost none. Building codes remain the first obstacle. Most jurisdictions use prescriptive codes specifying equipment types rather than performance outcomes. Financing creates the second barrier. Banks assess risk based on familiarity. the expertise gap forms the third barrier. 2 generations of architects learned nothing about passive cooling in school, but these barriers are cracking. California Title 24 now provides explicit credit for passive cooling strategies. Net zero building mandates spreading through major cities make passive cooling necessary rather than optional. For residential applications in appropriate climates, whole house evaporative coolers cost $3,000 to $7,000 installed, compared to $15,000 or more for central air conditioning. Operating costs run 3 to 5 cents per hour compared to 30 to 50 cents for compressor-based cooling. These costs make a big difference for homeowners. 3,000 years ago, Persian engineers mastered cooling without electricity. For 100 years, an industry alliance buried this knowledge, not because it does not work, but because it works too well. Passive downdraft evaporative cooling works by letting hot, dry air pass through a wet medium at the top of a structure. As moisture evaporates, the air cools, and that process, evaporation, makes the air denser so it naturally sinks down into the living space below. Start by identifying or creating a vertical shaft on the warm side of your home, ideally facing the prevailing wind. At the top, install evaporative pads or make a DIY cooling medium using thick cellulose pads, stacked burlap sacks, or coconut fiber matting. The key is a porous material with lots of surface area that can stay wet. Set up a water delivery system so the pads stay continuously moist. When hot, dry air passes through the wet pads, evaporation absorbs heat. The cooled air becomes denser, falls down the shaft, and flows into your living space through the bottom opening. Before you begin any construction, determine whether passive evaporative cooling will work in your climate. Check local humidity levels during summer months using weather data from the National Weather Service or a simple hygrometer from any hardware store for under $20. If your average summer humidity stays below 40%, you are in ideal territory. Between 40% and 60%, you will get reduced but still meaningful benefits. Above 60% humidity, evaporative cooling becomes largely ineffective, and you should consider other passive strategies such as thermal mass and night flushing instead. The simplest do-it-yourself approach involves constructing a downdraft cooler that mounts on your roof or attaches to an exterior wall. Begin by building a rectangular box approximately 2 feet wide by 2 feet deep by 4 feet tall using 3/4 inch exterior plywood. Frame the interior with 2x4 lumber for rigidity and seal all joints with exterior caulk to prevent air leakage around the cooling medium. Cut an opening approximately 18 inches square in the top of the box. Install a rain cap above this opening, leaving a 6-inch gap between the cap and the box top to allow air entry while preventing rain from entering. You can fashion this cap from sheet metal bent into a simple pyramid shape or purchase a standard chimney cap from a home improvement store. On one side of the box near the bottom, cut another 18 inches square opening. This will connect to your interior space through a duct or direct wall penetration. Install a simple damper or sliding panel over this opening so you can close the system during humid weather or winter months. Inside your box, you need a material that holds water and exposes maximum surface area to passing air. The most effective commercial option is rigid evaporative cooler pads made from cellulose, which you can purchase from HVAC suppliers for approximately $30 to $50 per panel. Install these vertically inside the box, leaving a 2-inch gap between the pads and the walls to allow air to flow around and through them. If you prefer a homemade approach, stretch burlap fabric across wooden frames sized to fit snugly inside your box, stacking 3 or 4 of these frames with 1-inch spacers between them. Alternatively, fill the box loosely with Excelsior wood shavings contained within hardware cloth cages, or use coconut coir matting wrapped around a wire mesh cylinder. At the top of your cooling box, install a length of 1/2-inch PVC pipe drilled with 1/8 inch holes every 2 inches along its length. Cap one end and connect the other to your water supply. Position this pipe so water drips evenly across the top edge of your evaporative pads. Below the pads, install a collection pan made from galvanized sheet metal or a plastic tray sloped slightly toward one corner where you will install a drain fitting. Connect this drain to a 5-gallon bucket or small reservoir positioned below the unit. For water recirculation, purchase a small submersible pond pump rated for approximately 100 gallons per hour, costing between $15 and $30 at garden centers. Place this pump in your reservoir and connect it via flexible tubing to the distribution pipe at the top. Plug the pump into an outdoor timer set to run for 15 minutes every hour during hot periods. If you want an even simpler gravity-fed system, position a covered 5-gallon bucket above the unit and run tubing from its bottom through a simple float valve salvaged from a toilet fill mechanism. The cooled AIR needs a clear path into your home, and stale air needs a way to exit. Cut an opening through your exterior wall directly below where you have mounted the cooling box, matching the size of the box bottom opening. Frame this penetration properly with treated lumber and flash it carefully to prevent water intrusion. Install a short section of insulated duct connecting the box to the interior, terminating in a standard ceiling register. On the opposite side of your home, install an exhaust pathway. This can be an existing window left partially open, a dedicated exhaust vent near the ceiling, or best of all, a solar chimney, a dark painted vertical shaft on the sunny side of your home that heats up and draws air upward through natural convection. For significantly enhanced cooling, consider installing a buried air intake pipe. Dig a trench approximately 4 feet deep and 50 to 100 feet long, running from a shaded area of your yard toward your home's foundation. Lay 4-inch or 6-inch PVC pipe in this trench, sloped very slightly toward a drainage point to prevent condensation accumulation. At the far end, install a screened vertical intake pipe rising above ground level with a rain cap. Connect the pipe to your home through the foundation or crawl space, terminating in a floor register in your main living area. Air drawn through this buried pipe exchanges heat with the surrounding soil, which maintains a nearly constant 55 to 60 degrees year-round at that depth. If you combine a buried intake pipe with a rooftop downdraft evaporative cooler, you can achieve temperature drops of 30 degrees or more below ambient conditions on hot, dry days. The ancient Persian systems worked partly because thick mud brick walls absorbed heat slowly during the day and released it at night. You can add thermal mass to your modern system by positioning the cooled air outlet so it flows across or through dense materials. Stack concrete blocks or stone pavers along interior walls in the path of the cooled airflow. Fill large clay pots with water and place them in corners of the room. Run your evaporative system during the hottest part of the day when humidity is typically lowest. In most desert climates, this means late morning through late afternoon. At night, in arid climates, open windows on opposite sides of your home to flush accumulated heat and pre-cool your thermal mass for the next day. Your thick walls, concrete floors, and water containers absorb this coolness and release it gradually through the following day. Monitor your evaporative pads or homemade medium for mineral buildup from hard water. Every few weeks, remove the pads and rinse them thoroughly or replace homemade media that has become clogged. Drain and clean your water reservoir monthly to prevent algae growth and mosquito breeding. A complete DIY rooftop downdraft cooler using the materials described above typically costs between $200 and $400. A buried ground coupled intake pipe adds another $300 to $600 if you rent a trencher or dig by hand. Compare this to operating a standard 3-ton central air conditioning system, which costs roughly 30 to 50 cents per hour in electricity. Running that system 8 hours per day through a 4-month cooling season adds approximately $300 to $500 to your annual utility bills, plus maintenance and eventual compressor failure. Before cutting holes in your walls or roof, check local building codes regarding penetrations, structural modifications, and water systems. Many jurisdictions require permits for any modification to your building envelope. Ensure any electrical components are properly rated for outdoor wet locations and connected to ground fault protected circuits. Keep water reservoirs covered to prevent mosquito breeding. You now possess the practical knowledge to build a cooling system that operates on physics rather than on perpetual electricity consumption. The principles are identical to those Persian engineers perfected 3,000 years ago. The materials are available at any hardware store. The industry made this knowledge difficult to find because buildings that cool themselves do not generate monthly revenue. But the physics never changed. Water still absorbs heat when it evaporates. Cool air still sinks. And now you know exactly how to put those principles to work. They buried this knowledge because it threatened their business model. Now you have it. When water transforms from liquid to vapor, it absorbs energy from the surrounding air. Scientists call this the latent heat of vaporization. At 30 degrees Celsius, that number is 2,430 joules per gram of water. In practical terms, evaporating a single gallon pulls roughly 8,700 British thermal units of heat straight out of the air. That is comparable to running a small window air conditioning unit for a full hour. Engineers map this process on something called a psychrometric chart. It tracks what happens when air meets water. The cooling potential depends on one critical measurement, the gap between dry bulb temperature and wet bulb temperature. The drier the air, the larger that gap, and the larger the gap, the more dramatic the cooling effect. In Phoenix, Arizona, at 105 degrees Fahrenheit and 15% humidity, evaporative cooling can drop incoming air by 25 to 30 degrees. In Denver, Colorado, at 95 degrees and 25% humidity, the drop still reaches 15 to 20 degrees. Now here is the number that changes everything. The American Society of Heating, Refrigerating, and Air Conditioning Engineers has documented that two-stage evaporative cooling uses 60 to 75% less electricity than conventional refrigerant-based systems. A bucket cooler with a small fan draws 30 to 50 watts. A window air conditioning unit draws 500 to 1,500 watts for comparable personal zone cooling. That is a ratio of 10 to 1, sometimes 30 to 1. The physics is not subtle, it is overwhelming. But here is what makes this truly remarkable. We did not discover this physics, we inherited it from civilizations that mastered it thousands of years before electricity existed. In ancient Egypt, around 2,500 BCE, frescoes depict servants fanning large clay vessels filled with water. Those vessels were made from marl clay found along the margins of the Nile Valley. Workers fired the clay at temperatures that left it porous. On hot days, water seeped through the walls to the outer surface where it evaporated. The air around each vessel cooled dramatically. Archaeological records also show Egyptians hanging reeds and wet cloths in doorways and windows. As desert wind blew across the damp fabric, the air entering their homes dropped in temperature immediately. A prominent feature of the ancient Egyptian house was a structure known as a malkaf, a triangular wind catcher mounted on the roof, opening toward the north. It captured the cooling breeze and funneled it down into living spaces below. 500 years before Christ, in ancient Persia, engineers built wind catchers called badgirs that still stand today in the city of Yazd. These tall, open turrets faced the prevailing wind. Air swept down into the structure and across underground water channels. The contact with water cooled the air, which then circulated through the home. Persian engineers perfected this across centuries. They created cooling networks that served entire cities in the middle of the desert. The Romans took a different approach. They pumped cold water from their famous aqueducts through the walls of elite homes to cool dwellings during brutal Mediterranean summers. In India during the Mughal era, builders hung screens woven from vetiver grass in doorways and kept them perpetually wet. These Q screens operated as living evaporative cooling pads for centuries. In the American Southwest, native peoples built homes from adobe and poured water over the thick earthen walls. The evaporating water cooled interior spaces through the same physics the Egyptians had discovered 3,000 years earlier. 5,000 years of proven engineering. Every major civilization on every continent independently arrived at the same thermodynamic principle. Then, in less than 1 century, it vanished from Western construction entirely. The machine had arrived, and everything that came before had to be erased. In 1902, a young engineer named Willis Carrier stood in a Pittsburgh printing plant solving a humidity problem for a lithography company. His invention became the foundation of mechanical cooling. By the 1920s, the Carrier Corporation had launched the Weathermaker campaign, positioning air conditioning as the symbol of modernity and progress. Their marketing framed evaporative and passive cooling as primitive and unsanitary. A Carrier engineering manual from 1930 dismissed evaporative methods as suitable only for cellars and agricultural storage. Industry publications celebrated the triumph of machine over nature as though dependence on electricity represented advancement rather than vulnerability. The shift happened fast. In 1927, the first model mechanical codes emerged with heavy participation from HVAC industry representatives. By 1945, the post-war building boom had standardized mechanical refrigeration as the only acceptable cooling method. Passive alternatives disappeared from architectural education entirely. The American Society of Heating, Refrigerating, and Air Conditioning Engineers codified mechanical cooling as the baseline for all thermal comfort calculations. By 1980, fewer than 3% of American architecture programs taught evaporative or passive cooling strategies of any kind. The technology was not disproven. It was not shown to be ineffective. It was systematically removed from professional memory. Contractors working today have never heard of evaporative cooling design because their licensing exams never mentioned it. Inspectors shaking their heads at blueprints cannot approve what their training never covered. Follow the money, and the picture becomes impossible to ignore. The United States residential HVAC market exceeded $15.4 billion in 2024. Globally, the air conditioning equipment segment generated over $130 billion in revenue that same year. Almost 88% of American households now rely on air conditioning. Every one of those units requires refrigerant refills and filter replacements and compressor repairs and eventual full replacement at $5,000 to $10,000 per system. Executives in corporate boardrooms and lobbyists in government hallways have built an empire on mechanical complexity. A $15 bucket with evaporative pads and a small fan cannot support a $130 billion industry. The physics works. The business model requires that you never learn it. The codes were written. The curricula were scrubbed, the industry locked in its revenue model, but there is one place where the consequences of this erasure are not abstract at all. They are measured in death certificates, and it begins with a question your landlord hopes you never ask. There is no federal law in the United States that requires landlords to provide air conditioning in rental properties. A Reuters survey examined housing regulations across all 50 states. Nearly half of states require landlords to maintain existing units, but not a single state requires that air conditioning actually be provided in the first place. The majority of jurisdictions classify air conditioning as an amenity rather than a basic requirement of habitable living conditions. Only a handful of cities mandate landlord-provided cooling. Tempe, Arizona, Dallas, Texas, Montgomery County, Maryland passed its law as recently as 2020. That is the entire list. In the rest of America, your landlord has zero legal obligation to keep you from overheating inside your own home. Now consider what that gap means in human terms. 2023 set the record for heat-related deaths in the United States. At least 2,300 death certificates cited the effects of excessive heat as a cause of death that year. Over 35 million Americans report living without any air conditioning at all. Census data shows renters at nearly 14% were significantly more likely than homeowners at 8% to experience dangerously hot conditions inside their own homes. Research from the New York City Department of Health confirms what many suspected. lack of access to home air conditioning is the single most important risk factor for dying from heat stress. Among those who died, the place of death was most often a home with no cooling, and this burden does not fall equally. A 2022 Boston University analysis of 115 metropolitan areas found that homes without cooling are most often occupied by low-income residents and people of color. Families staring at utility bills they cannot afford while temperatures climb higher every summer. Your landlord understands this equation even if the words are never spoken aloud. Installing air conditioning means capital expenditure, ongoing maintenance, and potentially higher insurance premiums. The renter pays the electricity, the landlord pays nothing. When pressed on the issue, landlord lobbying groups have told policymakers they would need to raise rents to cover the cost of upgrading electrical systems and adding cooling equipment. A $15 evaporative cooler built from a hardware store bucket threatens nobody's profit margin, which is exactly why no landlord, no property management company, and no HVAC contractor will ever suggest it to you. The codes are written against you. The industry profits from your ignorance, but here is what none of them can take away. The physics works regardless of what any landlord or building inspector or industry lobbyist says, and for the cost of a single pizza, you can build it yourself. One 5-gallon plastic bucket with a snap-on lid from any hardware store. One small battery-powered or USB fan between 8 and 12 inches in diameter. One sheet of evaporative cooling pad media made from cellulose or aspen fiber. A small submersible aquarium pump for continuous water circulation is optional. Total cost runs $12 to $18 depending on where you shop. Operating cost for 8 full hours of cooling comes to roughly 2 to 5 cents in electricity. Compare that to $1 or more per day for a typical 6,000 BTU window unit running the same period. The build takes less than an hour. Cut 3 to 4 circular ventilation holes in the side wall of the bucket. Each hole should measure roughly 2 to 3 inches in diameter. Roll the evaporative cooling pad into a cylinder and press it flush against the inner wall of the bucket. Every bit of airflow must pass through that wetted media. Mount the fan on the lid facing downward so it pushes air into the bucket from above. Air is forced through the saturated pad, and it absorbs the latent heat of evaporation. It exits through those side openings cooled by 10 to 20 degrees Fahrenheit depending on your local humidity. Now here is where honesty matters more than hype. This is not a replacement for whole house air conditioning. This is personal zone cooling, directed airflow that cools the person, not the entire structure. In dry climates across the American Southwest, the Mountain West, and the High Plains, this performs remarkably. In Phoenix, Denver, or Albuquerque, where relative humidity sits below 30%, the temperature drop is dramatic and immediate. But in humid climates along the Gulf Coast or throughout the Southeast, effectiveness drops sharply. The air in those regions already carries heavy moisture. High humidity slows evaporation. Slower evaporation means less cooling. That is not a flaw in the design. That is the physics telling you which tool fits which environment. Humidity management inside the room matters just as much. You must crack a window or provide an exhaust pathway. Evaporative cooling adds moisture to every cubic foot of air it touches. If that moisture has nowhere to go, humidity builds until evaporation stalls and the cooler becomes useless. Fresh air exchange is not optional. It is what makes the system function. Water consumption runs about 1 to 2 gallons per 8-hour session. Soak the pad thoroughly before first use for immediate cooling. Refill the bucket as water levels drop throughout the day. Keep the pad clean and replace it when mineral buildup reduces absorption. A well-maintained setup lasts an entire summer season on a single pad. Maintained properly, this system operates on the exact same thermodynamic principle that cooled Persian emperors, Roman senators, and Egyptian pharaohs. The only difference is the container. Every evaporative cooling pad, every wet cloth hung in a doorway, and every clay pot sweating in a desert window exploits the same 2,430 joules per gram that the Egyptians discovered 4,500 years ago. The water evaporates, the air cools, the physics has never once changed. For most of human history, this was simply how buildings stayed cool. Persians built wind catchers in Yazd that still function today. Romans circulated aqueduct water through villa walls on the Mediterranean coast. Native Americans poured water over adobe in the desert southwest. Mughal builders hung wet vetiver in every doorway across the subcontinent. 5,000 years of proven engineering spanning every continent. None of it patented, none of it metered, none of it billed to anyone monthly. Then in less than 1 century, an industry now worth over $130 billion convinced the Western world that the only way to stay cool required a compressor, a refrigerant charge, a licensed technician, and a monthly utility payment. They wrote the codes. They shaped the curricula. They sent lobbyists into government hallways and seated executives on standards committees. And they made certain that the simplest, most accessible cooling technology in human history never appeared in a single licensing exam, building inspection manual, or landlord obligation statute. But they cannot repeal thermodynamics. The water still evaporates, the air still cools, and for $15 at any hardware store you can build what 5,000 years of human civilization already proved works. The knowledge survived because physics does not care about marketing budgets, regulatory capture, or billion-dollar lobbying campaigns. It simply works. The physics has been waiting. It has always been waiting. Right now in Houston, Miami, New Orleans, and Singapore, millions of air conditioning compressors are running at full capacity. Not because the homes they serve are hot, because the homes they serve are wet. This is the secret the HVAC industry does not advertise. Your air conditioner was designed to lower temperature. That is called sensible cooling. But in humid climates, 60% of the energy your unit consumes goes towards something else entirely. It goes toward wringing water out of the air. Engineers call this the latent load. Your compressor handles it by overcooling air far below the temperature you actually want, forcing moisture to condense on freezing cold coils, and then sometimes reheating that air before it reaches your living room. It is the most inefficient thermodynamic process in your entire house. Engineers describe air using something called a psychrometric chart. Temperature runs along one axis, and moisture content runs along the other. Human comfort sits in a narrow band. That band is 72 to 76 degrees Fahrenheit at 40 to 60% relative humidity. Standard vapor compression air conditioning can only travel one path on that chart. It must cool in order to dehumidify, and it cannot separate the two tasks. This is not a flaw that a better compressor can fix. It is a fundamental thermodynamic constraint of the refrigeration cycle itself. Walk through neighborhoods in Galveston, Texas, in Baton Rouge, Louisiana, and in Manila, Philippines. You will see air conditioning units running 12 to 16 hours a day. You will see electric bills climbing past $300 a month. You will see mold crawling behind furniture and inside wall cavities. You will see dust mites thriving in the trapped moisture. Indoor air quality is collapsing even though the machine that is supposed to fix everything runs without stopping. Families are paying more money every year for a system that cannot solve the problem it was sold to solve. But here is what changes everything. Cooling and dehumidification are not the same problem. They require completely different physics. And 4,000 years ago, engineers on 3 continents already knew this. In the Thar Desert of Western India, temperatures reach 120 degrees Fahrenheit. Humidity during monsoon season climbs past 90%. Modern engineers would call this an impossible cooling challenge. Ancient builders called it normal life. Beginning in the 3rd century, architects across Rajasthan and Gujarat constructed elaborate subterranean structures known as stepwells. These played a significant role in defining subterranean architecture in Western India for over 1,000 years. The most famous is Chand Baori in the village of Abaneri, built during the 8th and 9th centuries. It plunges 13 stories into the earth. 3,500 steps descend into darkness. Tourists photograph it for its geometric beauty. Engineers study it for something else entirely. Temperatures at the bottom of Chand Baori run 5 to 6 degrees Celsius lower than at the surface. That difference matters. But the real engineering insight is what the water itself was doing. The massive surface area of exposed groundwater acted as a humidity buffer. In the chambers and galleries carved into surrounding stone, air circulated past cool rock and water surfaces that moderated both temperature and moisture at the same time. These were not merely wells, they were passive climate control systems that separated sensible and latent cooling using nothing but physics and stone. Then during British colonial rule beginning in 1858, officials declared step wells unhygienic. They called them breeding grounds for disease. Hundreds were filled in, sealed, or demolished across the subcontinent. An entire architecture of passive cooling was erased in the name of sanitation. The real engineering knowledge these structures contained was never studied, never preserved, never replaced. 5,000 miles west in what is now central Iran, Persian engineers had discovered the same principles independently. The qanats of Yazd stretched for miles underground, carrying water from distant mountain aquifers. But they served a dual purpose that modern archaeologists only recently understood. Air flowing through miles of underground channels did not just cool down, it dried out. Moisture condensed on the cool tunnel walls. Mineral deposits lining those walls, rich in calcium compounds, absorbed additional moisture from the passing air. The Persians had built desiccant dehumidifiers beneath the desert without ever using that word. At the far end of those qanats, cooled and dried air fed into yakshal chambers. These domed ice houses had walls 6 feet thick, made from a mixture of sand, clay, lime, goat hair, and egg whites. Archaeological teams with modern monitoring equipment have measured temperatures inside these structures holding at 25 to 30 degrees Fahrenheit through summers exceeding 115 degrees Fahrenheit outside. They stored ice in the desert for an entire civilization using nothing but physics. In Egypt, the principle appeared again. Natron, a natural mineral blend of sodium carbonate and sodium bicarbonate, served not only for mummification but for climate control. Underground storage chambers beneath temple complexes at Dendera show air passages routed over beds of natron before reaching food stores and living quarters. The natron stripped moisture from the incoming air. This is a desiccant dehumidifier. Egyptian builders were constructing them 3,000 years before anyone coined the term. Along the humid Malabar coast of Kerala in southern India, traditional Naluketu houses incorporated lime plaster walls embedded with sea salt compounds that absorbed excess moisture during monsoon season and released it during drier months. Measurements at restored heritage structures show interior humidity holding between 55 and 65% when exterior conditions reach 95 to 100% relative humidity. The buildings breathed. They self-regulated. No electricity, no compressor, no refrigerant, just materials that understood moisture. Every civilization that mastered hot and humid climates discovered the same two-part answer independently. Use the earth for cooling. Use minerals for drying. Persians, Indians, Egyptians, 5,000 years of convergent engineering across 3 continents. Then in less than 1 century, both halves of that elegant solution were replaced by a single machine that does both jobs poorly. To understand why the ancient solution works so well, you need to understand 2 separate physical processes that your air conditioner pretends are one. Sensible heat is the heat you feel. It is what a thermometer measures. Moving air from 95 degrees to 75 degrees is sensible cooling. The earth beneath your home, from 6 to 10 feet deep, holds steady at your region's annual mean temperature. In Chicago, that means 55 degrees year-round. In Atlanta, 62 degrees. In Houston, 68 degrees. That temperature does not shift more than 1 or 2 degrees across the entire year. Circulating water through pipes buried at that depth and then running it through radiant panels or a fan coil unit indoors handles sensible cooling with almost no energy. A small circulation pump from 50 to 150 watts, that is all. Latent heat is entirely different. Latent heat is the energy locked inside water vapor. Converting humid air at 80% relative humidity down to comfortable air at 50% releases enormous thermal energy. In tropical and subtropical climates, the latent load actually exceeds the sensible load. Your air conditioner handles this worse than anything else it does. The compressor overcools air to force condensation. It wastes energy reheating that overcooled air. It cycles on and off because moisture levels fluctuate independently of temperature. The machine was designed to make air colder. Drying the air is an expensive, wasteful side effect. When you separate these two tasks, something elegant happens. Each can be handled by a technology specifically optimized for that single job. Ground-coupled water loops achieve coefficients of performance approaching 20 to 30 for passive circulation because no compressor is involved. Desiccant materials excel at stripping moisture using only low-grade heat. Regeneration temperatures can be as low as 60 degrees Celsius. A basic flat-plate solar collector provides more than enough. The National Renewable Energy Laboratory has identified this separation of sensible and latent loads as capable of reducing total residential electricity demand by 25% or more in humid regions. Two problems, two solutions, each one brilliant at its specific task. The ancient world always treated these as two separate problems. Modern engineering rediscovered this in the 1930s, and then something remarkable happened. The solution was built, tested, proven, and then systematically buried. The closed-loop, hydronic half of this system is beautifully straightforward. High-density polyethylene pipe, 200 to 300 millimeters in diameter, buried in horizontal trenches at 6 to 8 feet deep, or installed vertically in boreholes reaching 100 to 400 feet down. A mixture of water and antifreeze circulates continuously through these buried pipes. As the fluid travels underground, it sheds the heat it collected from the building into the earth as constant thermal mass. The water returns cooled and flows through radiant ceiling panels, chilled beams, or a simple fan coil unit indoors. No compressor, no refrigerant, no phase change, just water carrying heat from your living room into the ground. The circulation pump draws 50 to 150 watts, less than a reading lamp. The ground loop itself lasts more than 50 years with zero maintenance. The first successful commercial ground source heat pump was installed in 1946 at the Commonwealth Building in Portland, Oregon. Nearly 80 years of proven technology sitting in plain sight. The Department of Energy confirms these systems use 25 to 50% less electricity than conventional heating or cooling. Indoor components last up to 24 years. The ground loop outlasts the building it serves. The desiccant wheel half is equally elegant. Picture a slowly rotating wheel about the size of a car tire. It is made of a honeycomb matrix impregnated with silica gel, zeolite, or lithium chloride. It turns at 8 to 20 revolutions per minute. On one side, humid outdoor air passes through the honeycomb. The desiccant material captures the moisture and holds it. Dry air exits and enters the building. On the opposite side, heated air passes through the same wheel moving in the other direction. That heat drives the absorbed moisture out of the desiccant and exhausts it outdoors. The wheel keeps turning. The drying never stops. The regeneration heat required is modest 60 to 80 degrees Celsius. A flat plate solar thermal collector, the simplest and cheapest solar technology, provides this easily from 4 to 6 square meters of collector area on your roof. The small motor that turns the wheel draws under 20 watts. This is a truly solar-driven regeneration. Now, put the two halves together. The desiccant wheel strips moisture from incoming ventilation air. The hydronic ground loop cools the building structure through radiant surfaces. The two systems share no fluid and no air path. They operate completely independently, yet they complement each other perfectly. The ground loop never has to deal with moisture, so there's no condensation risk on cooling surfaces. The desiccant wheel never has to cool the air, so it can focus entirely on drying. Each system does exactly one job and does it brilliantly. Total continuous electrical draw for the combined system is 100 to 250 watts. Compare that to a conventional 3-ton air conditioning unit pulling 3,000 to 3,500 watts from your electrical panel. Field research supports these claims. In tropical Malaysia, two-stage solar desiccant cooling systems delivered 27.9% to 33.9% energy savings compared to conventional air conditioning. Studies across 6 major Colombian cities demonstrated electrical power savings of 52 to 60.9% in every climate zone tested. A desiccant system installed at a hotel in Taoyuan, Taiwan, confirmed effective humidity control year-round, using rejected heat from existing equipment to regenerate the wheel. Published research documented up to 64.3% increase in coefficient of performance when desiccant wheels were integrated into building climate systems. It describes a system that uses 200 watts instead of 3,000 watts, that runs on sunlight and earth temperature, and that handles 100% humidity without breaking a sweat. So why has no one ever told you about this? In 1902, a young engineer named Willis Carrier stood in a Pittsburgh printing plant, solving a humidity problem for a publishing company. His invention became the foundation of mechanical cooling. By the 1920s, the Carrier Corporation had launched the Weathermaker campaign, positioning air conditioning as the symbol of modernity and progress. Their marketing materials explicitly called passive cooling techniques primitive and unsanitary. A 1930 Carrier Engineering Corporation manual dismissed earth contact cooling as suitable only for cellars and food storage. The machine had arrived, and everything that came before had to be erased. This was not an accident of progress. This was strategy. By bundling temperature control and humidity control into a single machine, Carrier created a captive market. You could not upgrade one function without replacing the entire unit. You could not separate temperature from moisture without abandoning the product entirely. Every household in America became a repeat customer, locked into a 15 to 20-year replacement cycle. Executives in corporate boardrooms understood exactly what they had built. The American Society of Heating, Refrigerating, and Air Conditioning Engineers codified this single machine approach as the baseline for all thermal comfort calculations. ASHRAE Standard 55 and Standard 90.1 provide no compliance pathway for desiccant hydronic systems. Not because the systems fail, because ASHRAE never created the framework to evaluate them. The absence feeds itself. Without a pathway, no domestic installations happen. Without installations, no domestic data accumulates. Without data, the Standards Committee cites insufficient evidence to justify creating a pathway. Lobbyists in government hallways nod approvingly. The loop stays permanently closed. The International Residential Code assumes all ductwork exists inside buildings. Section M16 requires ductwork materials with specific flame spread ratings and makes no provision whatsoever for earth contact air handling. A hydronic radiant cooling system paired with separate desiccant ventilation does not fit the template. When a system does not fit the code, inspectors shake their heads at the blueprints. When inspectors reject blueprints, contractors tear out freshly installed components. When contractors tear things out, nobody tries again. Follow the money and the picture sharpens. The Air Conditioning, Heating, and Refrigeration Institute spent $47.3 million on political activities in 2022 alone. In 2019, ASHRAE Technical Committee 6.8 rejected a proposal to create a performance pathway for earth tube systems. The committee cited insufficient domestic performance data, while 3 decades of European documentation gathered dust. Analysis of that committee's membership revealed 67% of the seats occupied by representatives from HVAC manufacturers. The residential HVAC market in the United States exceeds $29 billion annually. Every desiccant wheel installed is a compressor that never gets sold. Every ground loop is a condenser unit that never needs refrigerant recharging. Every solar collector regenerating a desiccant is a monthly utility bill that never gets paid. Systems that cost a few $100s in materials and run on 50 watts of electricity cannot support an industry built on $1,000 units consuming 3,000 watts. Fewer than 5% of American architecture and engineering programs teach desiccant cooling as a primary strategy. Contractors have never heard of desiccant wheels because their licensing exams never mentioned them. Building inspectors cannot approve what their training never covered. An entire field of proven engineering vanished from professional knowledge, not through failure, through deliberate exclusion. The codes are written against you. The industry profits from your ignorance, but here is what they cannot erase. The physics works, and across Europe and Asia, they never stopped proving it. At the National Renewable Energy Laboratory in Golden, Colorado, researchers have studied desiccant dehumidification for decades. Their published findings confirm these systems could cut residential electricity demand by 25% or more in humid climates. In 1999, NREL hosted a formal desiccant dehumidifier wheel test workshop at their Advanced HVAC test facility. The event was co-sponsored by the Air Conditioning and Refrigeration Institute, the Gas Research Institute, and the United States Department of Energy. The technology was tested, it was validated, it was documented in federal research reports, and then it was shelved. In Malaysia, where oppressive ambient humidity makes conventional air conditioning chronically inefficient, researchers investigated solar desiccant cooling for tropical buildings. Their two-stage system achieved a coefficient of performance of 0.84 and reduced carbon dioxide emissions by 256 kilograms per month compared to standard cooling. In a climate where compressors run 16 hours a day and still leave buildings damp, the desiccant system delivered dry, comfortable air using nothing but thermal energy from rooftop solar collectors. Across 6 major cities in Colombia representing climate zones from tropical lowlands to high-altitude plateaus, a comprehensive study demonstrated that desiccant systems outperformed conventional vapor compression in every single location. Electrical savings ranged from 52.2% to 60.9%. Not in a controlled laboratory, in real buildings dealing with real tropical conditions. In Taoyuan, Taiwan, engineers installed an innovative desiccant cooling system inside an operating hotel facing year-round humidity. They used waste heat from existing cooling equipment to regenerate the desiccant wheel, creating a hybrid that dramatically reduced moisture loads on conventional systems. Continuous operation in one of the most challenging humidity environments on Earth. Documented, measured, published, ground source hydronic technology has an even longer track record. The first commercial installation in Portland, Oregon dates to 1946. The Department of Energy confirms ground source systems reduce energy consumption up to 72% compared to electric resistance heating and cooling. System life for the buried loop exceeds 50 years. These are not experimental curiosities. They are proven systems with decades of government-monitored performance data from installations around the world, decades of global research, thousands of successful installations, monitored systems in hospitals and hotels and homes, operating year after year in the most punishing humidity on the planet. The evidence is overwhelming, and none of it changes the fact that in most of America, you still cannot get a permit for this system. So here is what you can actually do. The ground loop comes first. HDPE pipe, 200 to 300 millimeters in diameter, laid in horizontal trenches at 6 to 8 feet deep. A serpentine or slinky configuration maximizes surface contact with the earth while fitting a manageable footprint. Total pipe run of 150 to 300 meters depending on your soil type and cooling load. Clay soils transfer heat better than sand. The pipe connects to a simple fan coil unit or radiant ceiling panels inside the house. A small circulator pump moves the water 50 to 150 watts. That is the only electrical draw for the entire cooling half of this system. Material cost for the pipe runs $300 to $500. The excavation is the real labor. A rented trencher and a determined weekend gets the pipe below the frost line into thermal mass that does not fluctuate with the seasons above. Backfill with compacted sand for intimate thermal contact between the pipe and the surrounding earth. No air pockets, no loose fill that will settle into voids over time. The pipe must touch thermally stable soil on every side for maximum heat transfer. The desiccant wheel is the second component. Commercial silica gel wheels are available from industrial HVAC suppliers in sizes appropriate for residential airflow rates of 200 to 400 cubic feet per minute. The wheel sits inside a simple air handling box with 2 separate air streams. On one side, humid outdoor air enters and passes through the wheel. The desiccant absorbs the moisture. Dry air exits into your building. On the opposite side, heated air from your solar collector passes through the wheel, moving the other direction. That heat strips accumulated moisture out of the desiccant and pushes it outdoors. The wheel turns continuously. The cycle repeats all day. Regeneration heat comes from a flat plate solar thermal collector. 4 to 6 square meters of collector area mounted on a south-facing roof is typical. This is the cheapest solar technology available. It heats water or air to 60 to 80 degrees Celsius, more than enough to regenerate any residential desiccant wheel. On overcast days or at night, a small backup electric element or a standard gas water heater delivers the same modest heat. Total collector cost runs $500 to $1,500. The two systems share nothing. No common ductwork, no shared fluid. They operate independently. The ground loop handles temperature. The desiccant wheel handles humidity. A basic controller with a thermometer and a hygrometer activates each system according to its respective measurement. Total continuous electrical draw for the complete installation runs 100 to 250 watts. Annual operating cost in climates like Houston, Miami, or New Orleans is $40 to $80 for electricity. Compare that to $1,500 to $3,600 per year running conventional air conditioning in those same cities. For the permit process, describe your ground loop as a closed-loop geothermal heat exchange system. That language fits existing code pathways in many jurisdictions across the country. Describe the desiccant ventilation unit as a dedicated outdoor air system with enthalpy recovery. That is ASHRAE-recognized terminology. Detached buildings, agricultural structures, and workshops often face less regulatory scrutiny than primary residences. The words you choose shape how the system is classified and how regulators perceive it. Maintenance is minimal. The ground loop requires nothing for 50 years. The desiccant wheel needs annual inspection and media replacement every 5 to 10 years at a cost of $100 to $300. The solar collector needs its glass cleaned. Total annual maintenance runs under $100 and 2 hours of time. $200 a year to cool and dehumidify a house in Houston, in Miami, in Bangkok, in Mumbai, using physics that predates the pyramids and materials you can order online today. Every civilization that mastered humidity discovered the same two-part answer. Use the earth for cooling. Use desiccant minerals for drying. Indian architects carved step wells into the bedrock of Rajasthan. Persian engineers lined qanats with mineral deposits beneath the deserts of Yazd. Egyptian builders laid natron beds under temple complexes along the Nile. 5,000 years of convergent proof from 3 continents. The physics never changed. The desiccant still absorbs. The Earth still holds steady at 55 degrees. The knowledge survived because thermodynamics does not care about marketing budgets or code committees or industry lobbying. It simply works. You now know something that most licensed HVAC contractors in America do not. You understand a principle that ASHRAE does not teach and building codes do not recognize. The ground beneath your property is an infinite cold reservoir. The sun above your roof is a free regeneration furnace. Between those two facts lies a cooling system that costs almost nothing to run, produces no emissions, requires no refrigerant, and works precisely where conventional air conditioning fails most completely. In 100% humidity, somewhere beneath your foundation, the earth holds steady. It does not care what the humidity is doing above. It has been waiting since before your house was built, since before the building codes were written, since before the HVAC industry existed. It will still be waiting long after all of those things are gone. The only question is whether you decide to use it. Persians froze water in a desert. Stanford proved the sky is a heat sink that never shuts off. Purdue turned it into a can of paint. UCLA turned it into a roll of tape. The cooling industry profits from your dependence on systems designed to be replaced every 15 years. These techniques never disappeared. You were never told about them. The sky has always been free.